let's get down to business. Hopefully everybody's remembering their circuits. We're going to continue with our review today and try to trend towards some newer material as we go. But mostly I just want to make sure that everybody's got a nice intuitive feel for how to solve these circuits. I do want to clarify something I said before. This happens a lot in engineering where you learn certain skills and then you promptly learn a better way to do it. So for example, you learn mesh and node and in circuits 1, and mesh and node is actually pretty handy, right? I mean that's really the best and only way to solve these circuits by hand, so you should know them and there's value in knowing them. The difference is that once you've built that intuitive understanding, you sort of use a computerized tool to actually solve circuits. But that doesn't mean you shouldn't have an intuitive understanding or a mathematical understanding for how that process works. So I wanted to kind of continue a little bit today with our just circuit analysis intuition, I'll call it, and we'll see if we can build on that. So let me check my notes. So I actually want to start with the circuit that we drew before, basically the same one from Monday. So do we have was it 24 volts or 12? It was 12 volts, and then help me out. I vaguely remember the numbers. It was 4, 2, and then 1 and 1.
No, that was 4 again. It was 4 and 2.
4, 4.
And
2 and 2. Is that right?
Yeah.
Okay. And I believe we worked out that, so we said this is 12 volts. This one we said should have been 3. Is that right? 4? 4 volts. Is that really right? 4 and 4 is 2, 2, 6, 30. Yeah, 4 volts. And this is 2 volts. Okay, I agree with that. Grand. Okay. So, and we're starting to ask some interesting questions. Like, for example, I asked if we changed the resistor value here, would we draw more or less power from the power supply? So does anyone remember if we decrease that resistor, do we draw more or less power from the supply? More. And what's the intuition for that? Right. There's less total resistance, which means there's less. There's less stuff impeding the flow of current. So you can have more current. If you get more current out of the same power supply, you get more power. So really, if I decrease any one of those resistors, right, should it matter which one I decrease? No, right? If I decrease any resistor, the net impedance that the power supply sees will go down, which means that current will go up, which means that power will go up. Pretty cool, right? So I wanted to do a couple more intuitive questions here. So what if, okay, so let's say this 2 ohm resistor is actually a light bulb, okay? You can always model a light bulb as a little resistor, okay? It's basically, it impedes the flow of current. It's just that, the current that it impedes, instead of dissipating the energy, remember how we said resistors dissipate energy, I squared R? Technically speaking, a resistor dissipates current as heat. A light bulb you can think of it as a resistor that dissipates energy as light, right? Okay, so let's say this is a light bulb.
I have just a question.
Yeah.
So if we change while you are drawing out, if we change this, increase the resistance of that resistor, then the power is decreased.
Yeah. If I make any of these resistors bigger, there's more resistance to the flow of current. Okay, and then as you make it harder for electrons to get from here to there, you basically reduce the amount of power that gets drawn out of the supply.
So it's despite of its being parallel or in series connected.
Right. That's true. Right, it makes no difference. It doesn't matter if it's parallel or in series. More resistance just means less current. So for example, if okay, so let's start with this situation the way it is here. So I think we can agree that the more current that goes through this resistor, the more light shines, right? Right. So we can always say in general, more current equals brighter light. Fair enough? So obviously, if I change my power supply, right? If I go from 12 volts to 24 volts, is my light going to get brighter or darker? It better get bright. Put more power in, it better get brighter, right? So that's not a very interesting question. But here's an interesting question. If I take this resistor and I change it from a 4 to a 2, if I make that resistor smaller, is my light going to get brighter or darker?
Brighter because it's minimizing the resistance.
I thought you guys all took circuits 1. That's the whole point, right? It's not really intuitive, right? And I want to kind of develop a little intuition. I mean, one line of logic would be, if you make this resistor smaller, then there's going to be more current that's going to be drawn from the supply, and therefore more of that current might make it to the light bulb, and therefore will get brighter. I mean, that's one line of logic. Stay the same is an option. Can we argue that the light will get dimmer? Why would it get dimmer? There might be a case for that.
There's less resistance.
Because more current passes through
more
there.
current will flow through the less resistance.
More current passes through there.
Right. If this resistance gets lower, then electrons that make it to this intersection are more likely to want to go this way. Right? Because they always, they prefer the path of least resistance. So it could be the case that by lowering this resistor, you're going to divert more current into this path, which means less current in that path, which means the light gets dimmer. Okay. At this point, I think our best bet is we got to solve the circuit and see what happens. So basically, let's see if we can get this voltage. Let's revise this problem and get this voltage here. We know the current is always going to be this voltage divided by this resistor. So in our original configuration, we had 1 ampere, right? So now if we reduce this resistor to 2, let's see what happens. So actually, let me back up. In our original problem, the power supply, how much power was it producing? In our original problem? Right. The whole thing it was drawing, there were 2 amps coming out. So it was doing 24 watts, which we got was 12 volts times 2 amps. We got the first branch was doing 1 amp. So we'll say branch 1 was doing, we said 2 amps through 4 ohm resistor. So what was our I squared R in that case? I squared is 4 times R is 4, that's 16 watts. And through branch 2, we had 1 amp through a 2 ohm resistor and another 2 ohm resistor. And each one of those is giving me I squared R was giving me 4 watts. Each one of those is giving me 4 watts. Is that basically what the deal was? So this is the way the problem was before. There was 2 amps coming out of the supply. So this guy was producing 24 watts. This branch got one of those amps and therefore was consuming 16 watts. This branch got the other amp and therefore it was I squared R through each one of those, so it was 4 watts and 4 watts. I feel like I've missed something. 16, 2, 1. Ah, hold on, this isn't right, is it? Hold on a minute. Yeah, that branch only has 1 amp. 4. Yeah, hold on a minute. You guys got to call me out if I make a mistake. Don't wait for me to find it. Right? This was 2 amps. If 1 amp went here, then there was only 1 amp going here. So this resistor was actually consuming how much? How many watts? 4 watts, right? I squared R. If I is 1 and R is 4, that gave me 4 watts. So we had 4 watts, 4 watts, 4 watts. And how much power is getting burned through there? It's I squared R. That's the 16 watts. That doesn't add up.
Branch 2 shouldn't be. Yeah, that should be 2 watts. Yeah, they each be 2 watts. You only have 1 amp going.
Good, thank you. There we go. Now we're all on the same page? Okay, and then, so just for completeness, my 4 ohm resistor had 2 amps through 4 ohms, and that was my 16. Okay, so in our original configuration, it was 2 amps, 1 amp, and 1 amp. This resistor was consuming 16 watts, and then it was 4 watts, 2 watts, and 2 watts. And does the power all add up? Yeah, the supply is producing 24 amps. The resistors are consuming a total of 24 amps, so there's no power that's been unaccounted for. So that's good. Now that we remember the circuit, let's go and change this from a 4 to a 2. Okay, so let's resolve that circuit if we reduce that 4 ohm resistor to a 2 ohm resistor. And then we'll see how our intuition held up. So 12, 4, 2, 2, and 2. All right, so how are we going to do this? What's that?
You still have to find equivalent resistance.
Yeah, so we basically need to find the equivalent resistance to know how much current is coming out of the circuit. So what's the first step in finding equivalent resistance? Add those two. That gives me 4. And that'll give me a 4 in parallel with a 2. Okay, now watch this. I've got a 4 in parallel with a 2. Would you like me to see me get the equivalent for that without using a calculator? Okay. Kashi, can I do that? It's going to be 4/3, right? Right. So the trick I like to use is, you can't always use this trick, but sometimes it rears its head. Okay, whatever. The easy way, this problem is easy enough that you could just do it, right? It's product over sum. So the product is 8. The sum is 6. So that gives you 4/3. Okay, ohms. But the sneaky guy solution is to look at this 2 and say, if I had 2 4 ohm resistors in parallel, what's the equivalent resistance of like if you have 2 resistors that are the same in parallel? Half of that, right? So anytime you have R and R in parallel, that's the same as R over 2, right? So I could actually, instead of putting a 2 ohm resistor here, I could do 4 and 4, right? I mean, this is the same as a 2 ohm resistor. So now I've got 3 4 ohm resistors in parallel, 4/3. Yeah, whatever. Whatever, you're not blown. Your minds aren't blown. Okay. All right. So, all right, I got better party tricks. Don't worry. Okay, so we got 4/3 for these 3 resistors. Add that to the 4. So 4 plus 4/3. That's what, 5 1/3, 5 1/3, which is the same as 16/3. So your total impedance is 16/3. So if I were to draw the Thevenin equivalent for this circuit, remember that term? So how much current is being drawn from the supply? Come on, y'all. V equals IR. You guys remember that one? Okay, V is what? 12. I is the unknown. R is 16/3. I equals 36 over 16 amps. 2.25. All right. 32, 4, yeah, okay. So the one thing that we all seem to agree on is if I made that one resistor smaller, my total current was going to increase. And in fact, that did turn out to be the case. So my power supply is 12 volts at 2.25 amps. So now my supplied power is 24 plus 3 is 27 watts. Did I do that right? Is it 27? Well, I know 2 times 12 is 24. I know a quarter of 12 is 3. So 24 plus 3 is 27. That's how I got that. Okay, so that's good, right? Our intuition served us well. We know that decreasing any resistor means less impedance, means more current, which means more power. So that part worked out. Okay, so now let's figure out the branches. So 2.25, let's see, what is how much power goes through the 4 ohm resistor?
You're saying how much power?
Yeah, let's start by, I want to do like equivalent calculation to over here. I want to account for where everything goes. So how much power goes through that 4 ohm resistor?
8 to 1.
Right, so the power that goes through there is I squared R, which is 2.25 squared times 4, which is what? 20.25? Wow, so that really gets the lion's share of the current of the wattage. Okay, so now my 2.25 amps gets to this node, and it's got to decide where to go. So how much goes down and how much goes over? How do you reckon that?
I think 1/2 goes that and more goes through the least resistance.
Right. Which side gets more? This side gets more because it's less resistance. At what ratio?
Twice as.
Right. This is half the resistance of this. So this had better get twice the current. So in other words, what I'm going to do is I'm going to take this number, divide it into 3. So basically, 1/3 of this current goes through here, and 2/3 of it goes through there. Okay. So in other words, we had 2.25. If I divide that by 3, 0.75? Okay, so what is going on out there? So 0.75 goes to the right, and therefore holy smokes. You guys see what's going on out there?
Look at this window.
You know, I've taught in this classroom when it's been raining in the windows. You know, I thought I've done like every kind of environmental issue here in this classroom. But that was a first. Okay. All right, so we agreed that whatever the current on the right, this one had to be double it. So if that's 0.75, did I lose my mic? Down this branch has to be 1.5 because it's double that. Okay. Now let's see. There's another sanity check. There's another way we could have gotten the same answer. Let's just check this to make sure it makes sense. If I've got 2.25 amps going through this 4 ohm resistor, what's the IR drop over that resistor? It's a 9-volt drop, right? If you do V equals IR for this resistor, right, you take I times R. So if you take this number times this number, you get 9. So if this was 12 volts, this is 3 volts because you lost 9 volts across the resistor. And if this is 3 volts and this is 2 ohms, what's the current going through that resistor?
Current or the volt?
Sorry, what's the current going through this resistor? If this is 3 and this is 2? Right, it's V equals IR. 3 volts divided by 2 ohms is 1.5 amps. That's the same answer we got using the other method. So that's a good sanity check. Okay. Where is it? We got to work on that. Yeah, we'll fix it. Maybe I just need to wear thicker shirts or something. Okay. Cool. So, all right. So if that's 3 volts, what's my voltage going to be here? It's going to be half of that, right? I mean, of this 3 volts, right? There's 2 ways to think about it, but the easiest is probably if this is 0.75 amps, what's the IR drop across this resistor? It's going to be I times R, so 0.75 times 2, 1.5 volts. Cool. So, so through branch 1, so let's go do our math now. So through branch 1, now we have 1.5 amps through a 2 ohm resistor. So what's my I squared R for this branch? What's my power? No, let me do it. 1.5 squared is 2.25. Doubled is 4.5. Yeah, okay. Thank you. No, it's okay. I need more practice in doing my calculations. It's okay. So 4.5 watts went through. So did the power through branch 1 go up or down? Went down. That's interesting. Did the current go down? Oh, isn't that fascinating? Look at this. Well, let's finish all the numbers and then we'll compare and contrast because I think this is a fun exercise. Okay, now through branch 2, each of those resistors has 0.75 amps through a 2 ohm resistor. So what's my I squared R going to be for each of those resistors? 3/4 squared is 9/16. 9/16 times 2 is 9/8. So that's 1 1/8. 1.125. For each of them, right? Because there's 2 of them. Okay, so first questions first. Does all my powers add up? This plus this gives me 2 1/4. 2 1/4, 6 3/4, 27 watts. Good. So in other words, the power that's being generated by the supply is accounted for. It's being completely dissipated through the 4 resistors, which is good, right? You can never have all the power that you generate has to be consumed somewhere, right? Otherwise, you got big problems. Cool. Did my light bulb get brighter or less bright? Less bright. Huh. Let's see if any of our intuition made sense. Okay. So we agreed, we knew that more current was going to come out of the power supply. We were right about that. But then we didn't know whether, so we got more current, but then we said by making this smaller, that more current, maybe all that extra current will go down that branch and therefore make the other branch less bright. That was kind of our line of reasoning. So we started by generating, over here we had 2 amps, on that side we had 2 1/4 amps. Let's see, in branch 1 we had 1 amp. Now in branch 1 we have 1.5 amps. Okay, so that was actually the rationale that made the most sense. Okay, we drew more current from the supply, but by decreasing the value of this resistor, a lot more current went through it. Okay? And because current is I squared R, if you make current just a little bit bigger, the power that it burns gets a lot bigger, a lot more than just proportional. So we got a little bit more current through this resistor and a lot more power through it, right? It went from 4 watts to 4.5 watts. So we got a little bit more current, went through this branch, which means that even though there was more current being generated here, basically all the extra current we generated went through that branch. No, more than that, right? We generated, how much extra current did we generate? Right. Over here we had 2, over here we had 2.25. So we're drawing an extra 1/4 amp from the supply. But where did all that extra current go? It went into this resistor. Not only did the extra 1/4 amp go here, but also another 1/4 amp that was going through this branch now got sucked off into this branch because the resistance was so low. So basically this guy sucked up all the resources and the light got dimmer. And that's a neat problem, right? It's deceptive in that you kind of have to wonder about how all the pieces are connected, and you try to build a little intuition with this stuff. So yeah, the light gets dimmer, and that's the rationale. So what was the other line? What was the line of logic that would say this guy gets brighter? Oh, I think the rationale was just that if less resistance means more current, and if there's more current, then it's going to get brighter. So that turned out to be half true. There was more current coming out of the supply, but it all went through that resistor. Right? It got more power hungry. And it kind of makes sense, right? So one way that's always fun to solve these problems is that makes it easier to solve them rather, is you can take things to the extreme. So here's a way we could have really definitively answered this question without doing any math. So my question was originally, if I make this resistor smaller, what happens to the light? Brighter or darker? So one way that engineers like to think is, okay, you want to make this smaller? Let's make it as small as you can go. What's the smallest number I could make for that resistor? 0? Right, you can't have negative. You actually sort of can, but you need quantum physics and whatever. I did a summer project once in a lab, and I had negative resistances. It was more headache than it was worth. Okay, but whatever. Let's say 0. So so I say make this smaller. Does the light get lighter or darker? So let's make this resistor smaller, not just a 2, but to as small as it can go, which is 0 ohms. So what does a 0 ohm resistor look like? It's a short. Okay. So if I were to make this as small as it could be, I would replace it with a short. Okay, ready? Now, did my light get brighter or darker? It's off, right? All my current, once it gets to here, that's it. Show's over. There's no current going through this resistor. Because this is now, what voltage is this? What voltage is this? 0. What voltage is this? 0. See how they're connected with the wire? 0. Okay, so if this is 0 and this is 0, is there any current going through this path? No, there's no IR drop, right? You need V equals IR to get I, right? If V is 0, then I had better be 0. That's it. Lights off. So that's a cool way you could have answered that question without any math, without even doing all that song and dance we just did. You just say, okay, let's make that resistor get as small as it can be and then see what happens, right? So conversely, you could say, what happens if you made that resistor bigger, right? So what's the biggest resistor you could have? Infinity. What does an infinite resistor look like? Open circuit. Okay, there you go. There's your infinite resistor, right? Infinitely resists current. All right, so now in this case, what happens? There's no current going through this branch. Now all the current goes through that branch. How many amps are going to go through our circuit now?
All amps.
Amps reduce.
What's that?
The amperage reduces, but all the amperage is going through the pump.
Well, let's see. So what's my total impedance that is seen by the supply? I just add those together, right? 4 plus 2 plus 2 is 8. So the total current that's being drawn is 12/8. What is that, 1.5? Is that really 1.5? Yeah. Okay. So 1.5 amps is going to come out of here. But the difference is now there's no branch over here for it to go down. So it's all going to go through this path. So whereas before it was 1 amp, now it's 1.5 amps. Did it get brighter? Cha-ching. So good. So that's two pieces of the puzzle, right? If the resistance gets so low that it becomes 0, the light turns off. If the resistor gets so big that it's infinity, the light gets brighter, and that was an easy calculation to do. And so everything else between there is a shade of gray. If the resistor gets a little smaller, the light gets a little darker. Okay? If the resistor gets a little bigger, the light gets a little brighter, so on and so forth. And that's essentially the calculation we did. But those are tricks you can use for building intuition. Remember, any like code monkey can sit there and build circuits in multisim and hit the go button, right? What makes you valuable is you don't even need to do the simulation. You'd be like, yeah, of course making that resistor smaller is going to make the light, what did we say? Of course making that resistor smaller is going to make the light dimmer, right? Anyway, you don't need to run a simulation to see that, right? That's the kind of intuition I want folks to get comfortable with.
So when we had a short circuit, then we had a 3 amps going through the short circuit.
Right. When we did the short circuit, right, that's it. The total impedance seen by the power supply is 4. Okay, so that's it. You're drawing 3 amps, and 0 of it is making it to the light source. Good. Questions? Is any of this new? I mean, is this stuff you kind of talked about in Circuits 1, or maybe a little bit? All right. All right. Well, you need to see it my way in order for anything else to make sense. All right. A couple more questions. Let's put this back. What was this, 4 ohms before? Okay. So let's forget about the light bulb for a minute. I want to talk momentarily about the voltage divider story. We said this was 2 times 4 is 8. We said this was 4 volts, right? Okay. So when we talked about the voltage divider on Monday, did you guys do transfer functions? No. Okay, I'm going to take that blank stare as a no. Good. Okay, so when we talked about voltage dividers, so we had V supply. You want to call this R1, or what do we call this on Monday? R1 or R2? R1. R1. Sweet. R1, R2, V out. Do we need to resolve this circuit every time we see it? No. Okay. Always V out will equal R2 over R1 plus R2 times V supply, or V source, or whatever you want to call it. Now, knowing that, I want you to look at this circuit. So, starting from here, right, so if you ignore everything to the left of this resistor, okay, does this, so we've got, let's say, the left-hand circuit and the right-hand circuit. Does the right-hand circuit obey the voltage divider rule? Sure it does, right? My V supply is 4 volts. So I've got 4 volts times 2 over 2 plus 2, right? So for the right-hand circuit, I've got V supply is, let's see, R2 is this guy, 2, over the sum of them, and I'm going to multiply that by my V supply, which is 4 volts. So what does that math give me? Right, 2 over 4 is a half. Half of 4 is 2 volts. Is that what I get? Hey, that's kind of slick. Okay, so even in this case where it's a little bit more sophisticated, the voltage divider still applies. It's kind of slick, right? Now, what if we talk about the left-hand circuit? Again, trying to build intuition here. So if I look at my left-hand circuit, I've got a V supply which is 12 volts. So if I write my voltage divider, I've got my R1 is 4, my R2 is 4. So what if I say 4 over 4 plus 4 times 12? What does this calculation give me? 6 volts. But that's not what I got.
I think if you use like a loop method, you can get that.
First of all, do we see what the conflict is? I'm trying to paint a picture here. First we came along, we said, hey, voltage divider, look at this. If you remember this, it saves you a lot of time because then you don't have to do like 3 calculations every time. You just recognize it and do it once. So this is handy. And then I said, look, it's so handy that you can use it to solve this circuit. Right? You look at this circuit and you say, okay, 4 volts, 2 ohms. Oh, it worked out perfectly on the right-hand side. See how useful it is? But then when I tried to apply it to the left-hand side, it fell apart. It does not work. The voltage divider equation predicts 6 volts, but we know in actuality, because we've solved it, the right answer is 4 volts. So I want to know why. What is going on? Yes? You're not accounting for the right side of the circuit. Good. So what do I mean by that? Let's say, for example, that I just built this circuit. So 12, 4, and 4. Yes?
So that's going to be a voltage divider. Well, I guess the voltage divider won't actually work for, you're going to have a resistance on your output.
That's right. Right. The voltage divider assumes that all the current that goes through this resistor goes through this resistor. That's how we did the calculation, right? Well, when voltage divider was derived, literally the way we derived it is that all the current that went through R1 went through R2, right? As long as that assumption holds, we're golden. It'll totally make sense. That's why when we looked over here, it worked on the right-hand side because all the current that goes through that 2 ohm resistor also goes through that 2 ohm resistor. Now on the left-hand side, it's a different story. I got current going through this 4 ohm resistor, but does it all go through this through the down branch? Of course not. So let's start with this. 12, 4, and 4. So what's my voltage going to be at this node? That's your voltage divider equation, right? It's going to be evenly divided between the 4 and the 4, so we get 6 volts. Now, I'm going to come along and add my other 2 resistors. By adding resistors, is there going to be, what should happen to this voltage if I add resistors? It's going to drop. Let's have an intuitive reason for why that voltage should drop if I add resistors. Yeah, go ahead.
I was going to say, do we have to overcome voltage divider problems like that with the voltage changing? It's just put it into like a base of a transistor or something.
Yeah, I was going to get to that. We'll deal with that. Yes?
With the extra resistance on the circuit, there's less current going through, so there's not going to be as much.
There's less current. Right, that's exactly. So there's a couple ways we can think about this. If I slap extra resistors on there, then what's going to happen to the current coming out of the source? More current or less current? Less current. Less current means everything gets smaller. Okay, so that's one way to think about it. Here's another way to think about it. If I put some resistors here, those resistors will be effectively in parallel with this resistor, right? With the 4 ohm resistor. Will that make that resistance go up or down? So in other words, essentially what I'm starting with is a 4 ohm resistor, and now I'm going to put some other baloney with it in parallel. Okay, so this is 4, and this is whatever I'm adding in parallel. So if I put some other resistance in parallel with that 4 ohms, let's think about the range of values that could happen. Can this parallel resistance ever be more than 4 ohms?
Less than the least resistance.
It's got to be less, right? So, okay, here's how you can think about this. You can either do the formula, which, forget the formula. Okay, so what's the smallest this resistor could be? 0. If this was a 0, what would be the parallel impedance of those two? All right, if I put a 0 ohm resistance in there, what will be the total resistance of that parallel combination? 0, because any electron that gets here is going to say, screw going through the 4 ohm resistor. Look, there's a free ride around this way. Okay, there's no impedance in this path. So there's no parallel impedance. So the smallest this parallel resistance could ever be is 0 ohms. What's the biggest it could ever be? Right. The opposite is if I put such a big resistor here that this was an open circuit. So what's the parallel resistance of 4 ohms in open circuit? 4 ohms, because every electron gets to this intersection and it says, dude, we can't go this way, right? There's no path. We've got to go through the 4 ohm resistor. So that's it. It just sees the 4 ohm resistor. So by putting something in parallel with the 4 ohms, that value is going to be, now the new parallel resistance is going to be less than 4 ohms. Right? It's going to be either 4 ohms or less. So the whole question I'm trying to motivate is, should we expect that 6 volts to go up or down? Okay. Well, what I'm telling you is, when we add another branch here, effectively this resistance goes down. And what happens if that resistance goes down? Right? It's still, it's R2 over R1 plus R2 times 12 volts. Okay, R1 is 4. So if R2 gets smaller, what happens to that ratio? What if R2 goes all the way to 0? What do I get? Then I get 0. And what's the biggest R2 can be? No, R2 can't be infinity. The biggest R2 can be is 4. So if R2 is 4, then you're back to 6 volts. So this number has to be somewhere between 0 and 6 volts, depending on what you put here. So it had to go down. There's no way it could go up. It's not bad, right? No math, just thinking. All right. Okay, let me tease the next section, and then I think on Friday I want to work some I've got some fairly hairy problems from the book that I thought we could try working, but yeah. All right. So let's say, for example, let me go back to this. Let's stick with this problem for a minute. Let's say I still want to have this circuit with the 2 branches, but I really, really, really want to have this be 6 volts. I still want to connect the voltage divider there, but I don't want any current to get sucked through this branch. I still want this to have 6 volts. Can anybody think of how I could use an op amp? Yes?
Op amps would be used to go above a certain voltage, and then it'll compare to the other voltage on it, and it'll put the source voltage out.
Too complicated. Sort of, but too complicated. All right. Everybody remember op amps? Op amps got like 2 rules, right? What's the 2 rules? inverted or non-inverted? All right. Yes, thank you. That's the first one. No current goes into an op amp. You can connect whatever you want to this, right? The op amp will melt before current goes into it. Actually, the op amp will melt when current goes into it, okay? Whatever you connect to it, it will not draw, no current flows in. It has an infinite input impedance. Okay, so no current flows in. Yes?
So it also has a virtual short.
It also has a virtual short. How do you mean? You're not wrong. I just want to know, how do you mean?
There's zero current, so at the negative, there's going to be zero current there as well.
Sort of. Okay. So, okay. Let's hold the thought on this. I'm essentially motivating a solution to that problem, but we are going to talk about op amps for the last 5 minutes of today, and then into what's next? Friday. Good. Okay. So op amps. The way I've drawn it, yeah. Almost. Not the two inputs. Okay, so op amps work like this. You've got two inputs, a V positive and a V negative, and you've got an output. Now, the rule is always that the output of the op amp is equal to some big old gain, some big old multiplier, times the difference between V plus, between the difference between the two nodes. So you take whatever the voltage is on this node, minus whatever the voltage is on this node, times it by some great big number that's a property of the op amp, and that'll give you your output. Fair enough? Now, this formula is always true. However, we never use it, because it's impossible to use an op amp in what's called an open loop configuration. Right? If an op amp is open loop, there's no connection between the input and the output. Okay? No connection between input and output. It's very, very hard to use an op amp in an open loop configuration, to the point of being impossible. So instead, we use a trick. We use what's called a negative feedback configuration. When you have a negative feedback configuration, essentially what that means is that the V minus connects somehow to the output. If you have the negative feedback configuration, something wonderful happens. Instead of being forced to deal with this equation, which is really unwieldy for a lot of reasons, you instead get a much easier equation. And that equation is that you get the virtual short that somebody was mentioning, which is that V out basically, the V positive and the V negative inputs wind up having basically the same voltage, almost exactly. Or rather, close enough that we can't measure or really even care about the difference. So, two rules for op amps. One, no current ever flows into the inputs. And two, provided it's in a negative feedback configuration, which it almost always will be, you can assume that the outputs have roughly the same voltage. Sorry, but the inputs have roughly the same voltage. If anybody cares to see the derivation of where this comes from, I'll be happy to show you, like during office hours or something. It's actually kind of cool. But I don't want to get into it now. Like, we'd fill 3 boards and but put you all to sleep. Okay, so here's what I want you to think about between now and when we start class on Friday. So suppose I have an op amp and I connect it like that. Is this a negative feedback configuration? Is V out connected somehow to V minus? Yes, it is. Okay, so I've got, I'll call this V in. And V out. Don't yell out the answer. What's going to be the relationship between V in and V out? It would seem that way. What's the relationship between V out and V minus? Look at the picture. What's the relationship between V out and V minus? They're the same. I wired them together. Exactly the same voltage. And because I'm in the negative feedback configuration, what must be the relationship between V minus and V plus? So now, what I've created is an amplifier in which my output equals my input. Isn't that cool? Why on earth would I want an amplifier that does nothing? Does it do anything? My output voltage is the same as my input voltage. Does it do anything? Ah, it gives the same voltage, but it blocks current. I'm just going to write that down, and then we'll talk about what that actually means on Friday. Blocks current.
So you mean, is it like acting as a like fuse or something?
It's not a fuse. It's actually, the fancy pants word for what it's doing is acting like a buffer. Okay, we'll talk about that on Friday. I'm going to leave it there. I've run over. Thank you. Your lab will be posted probably hopefully by the time class starts on Friday.